Good morning, everyone. Hello, Songwoo. Can you hear me? Oh, yes. Very nice. Chun-san, how was your weekend? What did you do? Songwoo, can you tell me what did you do over the weekend?
야, 안녕하세요, 교수님. 성욱이가 지금 마이크가 잘 안 돼서 제가
So, what was your weekend?
hello. My weekend was very loose, I guess. I was in the lab and then I met some friends in KAIST, and yes, I had some relaxing time also.
Okay.
Yes.
So, you finished your midterm exam?
Oh, yes, sir. Yes.
Okay, you are smiling. It seems that you did good work for the midterm exam. Um, uh, Today, I'm going to talk about a very popular machine learning model that is called convolutional neural network. I'm going to give you the basic structure of the CNN, and briefly, I will talk about the backpropagation chain rules. Especially CNN is developed for image classifications. For example, if you are writing characters like alphabet 1, 2, 3, 4, 5, 6, 7, 8, or English alphabet, this CNN will uh, classify that. So RNN is usually used for classification of text input or natural language processing. But another important part of our brain is uh, identifying the images and recognizing them and interpreting them. So because of that background, CNN is very important part of machine learning model. I'd like to shortly introduce the basic structure of CNN in this slide. It has convolution layer. Later on, I'm going to give you the mathematical operation of convolution. Then it's gonna have pooling layer. Pooling layer has maximum pooling or average pooling. Usually, pooling layers function is to achieve data reduction, because eventually, if you want to classify the images, output will be simple vectors. So it has to go through the data reduction processes, and the pooling layer is doing that function. This convolution and pooling layer is becoming a building block. Sequentially, this convolution and pooling layer building block are repeatedly connected in series. After more than maybe 100 or 200 layers, at the end of this network, we have fully connected layer. For example, if your image is numerical number like 1, 2 to 9, a fully connected output will have 10 different output from 0 to 10. And to produce the probability and classification, output function will be softmax function, and that output function will be labeled as y. Of course, we have true value y dash. By comparing y and y dash, we can define the cost function. With the given cost function, we can achieve the backpropagation. Of course, we have to know the connection of convolution layer and pooling layer, convolution and pooling layers, we have to find the paths to go back from cost function to softmax function, fully connected function, and pooling layer, convolution layer. So back propagation paths are in the reverse direction from cost function to last convolution layer. The function of convolution, as I mentioned before, a function of pooling layer is for data reduction. In order to reduce the burden of computation and memory, pooling layer are needed. However, let's talk about the function of convolution layer. And convolution is multiplication of input vector with the filter vector. Later on, I'm going to explain that. By applying those convolution function, what we can do is the feature extraction. At the beginning of machine learning of CNN, this convolution at the early stage of this CP building block connections, convolution will probably can extract the edge of the image. Probably as we move on, at the middle of convolution, maybe we can extract the shape of the image, and maybe next we can extract the object, and finally we can identify the images at the fully connection layers. Once again, I would like to say that convolution of function of convolution is for feature extraction, and function of pooling layer is to reduce the data. So sequentially, this CNN structure will conduct feature extraction and data reduction. Repeatedly, this operation will be applied to the image, and at the end, we can achieve the very accurate classification of the images. I think these are the overall introduction of the structure of convolutional neural network. You remember that RNN and LSTM is usually for classification of sequential data. So the previous stage information is carried to next stages through the hidden layers, and hidden layers are connected in RNN using W matrices. However, in LSTM, cell state, CLL state vector has large size and it contains a lot of information. And that cell state information is updated at each sequential stage. And finally, we can produce sentences or classifications, or it can do the machine translations. However, in CNN, this convolution and pooling layers are sequentially connected, but there is no timestamp. It is the single step images and output will be the classification. But however, we can put this CNN in serially. Probably we can combine CNN and RNN to achieve sequential image interpretation. That hasn't come to the reality yet. Probably some group of people in company or university are doing those researches. I'm sure that in a year or two, someone will introduce a new research by combining CNN and RNN. Now let's focus on the CNN right now. As I told you before, convolution is basic operation of CNN. So I would like to talk shortly about the CNN operation. There are another famous CNN, that is cable news network. But in this, maybe ordinary people may know more about cable news network. But in this class, we are going to talk about convolution neural network. As included in this word, CNN, C is most important uh, meaning in CNN, and that is convolution. Convolution is mathematical description of function or matrix multiplication. There are many cases in engineering and mathematics who are using the convolution operations. But in CNN, convolution has a little bit different meanings. And I'd like to introduce the convolution operation in CNN. Let's assume you have an input vector. Let's assume you have an input vector, input matrix that could be the image, very simplified image matrix. Usually image is the two-dimensional because when we are seeing object, the light is coming in parallel. So in our eye, the sensors are two-dimensional. Light is coming in parallel. We have sensors. So the sensors are two-dimensional. Also, the TV or papers and image representation in electronics also has two-dimensional arrays. Sensor itself is a two-dimensional array, and our screen is also usually two-dimensional array. Why is that? Because the light is coming in parallel. We are seeing the object by seeing the reflection of light. Usually, if the object is a little bit longer distance, usually we can regard that light beam is coming to our eye in parallel. But sometimes that's because that's why our image data can be described by two-dimensional array of data. However, even though we are seeing object in two-dimensional way, it may have different colors and different light intensity. So it has additional information is included in two-dimensional array vector. So we can add another matrices. So this kind of n-dimensional matrix is called tensor. But for the simplicity of class today, we are not going to talk about the multi-dimensional matrix information. Right now, we are going to only talk about two-dimensional data array, which include the information of the images. If we apply the convolution of image data with the convolution of filter, I would say this is filter, convolution filter. It has W11, W12, W21, and W22. This is very simple case. If we multiply this input data with this convolutional filter, output will be like this. X11 multiplied W11 added by X12 multiplied 12 additionally added by X1, X21 and X21. And then finally X22 and W22 is multiplied and this term is added. So convolution of this input data with this filter would be a single scalar number. This convolution filter is two-dimensional array matrix, and input data is two-dimensional matrix. Multiplication of these two convolution of these two matrices will be a scalar number. It is a kind of dot operation of vector in two-dimensional way. So this is becoming scalar. And then we apply the activation function. There are many different type of activation functions. You remember that we usually use the sigmoid function, or we use the tangent hyperbolic function for the case of RNN and STM. Here in CNN, we usually use ReLU function. ReLU is the kind of nonlinear function, and if the input is below zero, it's becoming zero. If the input is over 0, it will be proportional to input. This is a kind of nonlinear the activation function. You remember that in sigmoid function, it is the transition. It has a 0 to 1 transition, and at the far end, derivative of this sigmoid function is nearly becoming a 0. We need to have certain derivatives numbers to make an efficient backpropagation at those edges. So tangent hyperbolic function or sigmoid function usually has vanishing gradient at edge of the input stream. But however, in ReLU function is just linear function, is a linear function. So in this area, we do not have any gradient, but in this area, we have a proportional to gradient. So we still have the gradient. So because in the backpropagation, we have to go through many layers of pooling and convolution to keep the gradient from the end to the beginning. ReLU function is aimed to be useful in CNN machine learning model. So in CNN, people are usually using the ReLU function for the activation function. So now I'm talking about convolution operation in CNN. And convolution, as I mentioned before, convolution is repeatedly applied in the sequence of these hidden layers. And convolution function is to make a feature extraction. At the beginning, a large scale feature, rough feature will be extracted. At the end, it will have more object or identity extraction will be performed. So now, as I explained just before, if we apply the convolution of a matrix with the filter matrix, we're gonna have a scalar number by doing the dot product of each element of the matrix, and then finally we apply the activation function. That is gonna be the convolution operation of CNN. You remember that this W11, W12, W21, and W22 will be determined during the training process. Initially, we may assign certain numbers for W11, W12, W21, W22. But during the training process and backpropagation, automatically this W will be updated. And you remember in RNN case, we have U matrix and W matrix and V matrix, or there may, in LSTM, there are a lot of W matrices, output matrices, input matrices, and filtering matrix. There might be many gate matrices. And during the backpropagation, these parameters will be determined. And usually we are using the gradient descent method. Here also, in convolutional neural network, at each state of the convolution layer, we have filter. And this filter will be updated during the training process by applying the gradient descent of backpropagation. In this slide, for the purpose of the class, I'm just showing you only 2x2 filter matrices. But in complicated case, this matrix could be 1,000 by 1,000 or million by million to make it more clever CNN. Now let's assume that we have a 6 by 6 input vector, input matrix of image data, and that now let's assume we assume 2 by 2 filter matrix in CNN. Then by applying this convolution to this area of input vector, we can calculate by applying this scalar multiplication, and by applying the active function, we can calculate only this part. Then we can shift this window, this filter, we can shift one step by one step by one step. We can calculate the next cell, and then next cell, and next cell. The amount of movement for each convolution step is called stride. S. Sometimes S could be 1, sometimes S could be 2. These are, I think, kind of hyperparameters. Initially, you tried certain stride numbers, and you try that, and probably there might be trial and error. That these are kind of heuristic approaches. So when you are starting to build up your own CNN, probably you can look at some previous researches by looking at textbooks or open libraries or paper publications. Then you can start with them. Probably you can modify them. And these W's will be determined during the backpropagation. However, this slide will be determined by experience. These are the hyperparameters. And so the input vector, let's assume it is a 6 by 6, and your filter size 2 by 2. Usually we can output matrix will be 5 2 by 5. 5 is 6 minus 2 plus 1. These are very simple calculation. And sometimes we are adding some numbers at the input matrix, and to make a certain size of the output vector, we need to add some zeros at the edge. And this is called padding, zero padding. So in order to complete the convolution operation to adjust the input vector size, filter size, and output vector size, we have to decide the padding, how many zeros will be added at the edge of this input matrix. And also we have to decide the filter size, 2 by 2 matrix. Also, how much steps we're gonna move at each step. Here is the case of stride number 1. So also we have to decide the stride number. These are short introduction of convolution operation. As I said before, the CNN has this repeated structures of a building block. A building block has convolution layers and pooling layers. And the convolution layer function is to make a feature extraction. And at the end, this output matrix will be connected to fully connected matrix, and applying the softmax, we can identify or we can classify the input images. Now let's talk about the pooling operation. As I said before, major object or goal of this pooling layer is the data reductions. In this simple case, I just assume 2 by 2 matrices, but as more and more applications, this input size will be huge numbers. So in order to reduce the computational burden of computers, sometimes we need to do the data reductions. Yes, this is the another, again, the simple expression of the convolutional operation. And input unit cell, number one, this part is convoluted. Oh no, this number one part is convolution. Apply the convolution, and then we can get this element. If we apply this convolution at this part, we're gonna get numbers at the output vector here. If we apply the convolution operation at this section of input matrix, we can calculate number 6 element of this output matrix. Of course, we have to apply the activation function. These are the overview. There are two purpose of convolution operation. Main operation is the feature extraction. Of course, also the size of the input vector is changed to a small number of output vector, output matrix. So second purpose of this convolution operation is the downsizing of input images. Now let's talk about the pooling, and especially I'm gonna talk about max pooling. If the input vector has x11, x12, and x21 and x22 2x2 matrix, max pooling operation of this input vector matrix will be maximum number. For example, let's assume the input vector is 3, 4, 5, 6. If we apply the max pooling, output number will be 6. We choose the just maximum number. If you apply the average pooling, then output of pooling of this input vector will be 4, 3, 4, 5, 6. So it is very clear and evident that pooling operation of input matrix will be just scalar number, and of course the 2x2 matrix will become one-dimensional scalar number. So main purpose of pooling is definitely downsizing. Of course, during your design of machine learning neural network model, so hyperparameter you have to decide is the size of this window. This window has to be decided, and also heuristically you have to decide whether you will apply the max pooling operation or average pooling operation. Of course, as I explained in the previous slide, while I'm talking about the convolution here, pooling operation is the same. If you apply the pooling operation of window 2x2 here, then this number 1 section will be transmitted to number 1 element at the output matrix. If you apply the pooling window at number 3, it's gonna be transmitted to number 3 element of output matrix. If you apply the max pooling at section 4, it's gonna be transmitted to number 4 element of the output matrix. In this case, this is the case for stride number 1. If we have stride number 1, number 2 window will be moved to the next stage, next section of the input matrix. So also we can decide the number. Sometimes we can add the zeros at the edges. Maybe we can do this. We can apply the pooling operation. So now, up to now, I explained the basic structure of CNN machine learning model. And also I was talking about what is the operation of convolution and what is the operation of max pooling. Now, I would like to introduce uh, some of the famous uh, CNN model. That name is called LeNet-5. This is a really good start of the CNN, and it was introduced by Professor LeCun at, I think, Toronto University in 1998. Since then, CNN started to take an attention, and by combining the CNN model with GPU power and computing power, right now we have a lot of significant progresses of CNN model. So now the classification accuracy of CNN sometimes is more than 90% accuracy, and sometimes it could be better than human being. So by combining the CNN with computing power, probably our eye and brain can be replaced by computer. It has this structure. At the time, this LeNet-5 was intended to identify number writing. I'm writing 1, 0, 1, 2, 3, 4. Probably on the globe, there might be millions of people who may have different writing styles. But still, if the child is elementary school student, first year elementary school student, they can recognize 0 to 10, 0 to 9, even though different people have different writing styles. Logically, it is very difficult. For the example of 1, somebody can write that down like that. I can do that. Maybe there might be many different way of doing the writing number 1. But logically or mathematically, it is very difficult to explain why this is number 1 and why this is number 1 like that. So this LeNet-5 is trying to develop CNN model which can classify the writing of numbers. Input image has 32 by 32 pixel. So size of input vector is the 32 by 32. I remember that at the first convolution, I think it has 6 convolution and 6 pooling. So CV, convolution pooling, I remember LeNet has 6 pairs. Recent CNN may have 100 or more than that. And also I remember that when AlphaGo was, Google was developing AlphaGo, they used also CNN. And by combining CNN with reinforcement learning, they could develop the AlphaGo. And probably next month, I'm going to introduce some machine learning model of AlphaGo. That very fundamental structure of the classification model used in AlphaGo was CNN. In this case, we are using 32 by 32 images, but in AlphaGo case, they are using 19 by 19 and multiplied by n. N is the more information, so it's a kind of tensor, because the Go plate has the 19 by 19 grid, so it has this size. But here we have 32 by 31, 32. Oh, I'm sorry. Here we have 6 filters. In convolution operation, we had these filters, and that filter in LeNet, they used 6 convolution filters. By applying each filters, and in each filters we have unknown parameters, weight parameter wij, and that has to be decided during the backpropagation. And so by applying the 6 different filters, we have 6 different output. So let's assume this small square is the filter size. By applying the filter and doing the stride, and by applying the filter on here convolution, we can obtain this number. By moving these filters around the input image, we can get 28 by 28 matrix. And by applying 6 different filters, we were able to have 6 different images. So input image is just 32 by 32. At the convolution layers, by applying 6 different filters, we are obtaining 28 by 28 images of 6 different vectors. So it's becoming a tensor. Then we apply the pooling operation, and pooling operation means we have certain window, then maximum number will be obtained and write it down to the next output. Of course, here we apply the ReLU function, and then the size of 28 by 28 matrix is changed to half size 14 by 14. Now also at next stage, at this moment I do not have very precise numbers, but we also applying the convolution, maybe 16 different convolution, and the size of image is changed 14 by 14 to 10 by 10. And by applying the pooling, we obtain 5 by 5, very small size. So initially, the input matrix was 32 by 32. And after this pooling layer, our output size is matrix size is 5 by 5. And the number of layer was 16. And then each element is connected to fully connected layer. Of course, during this fully connection, we also need to find the weight. And then we have 84 fully connected elements. And at the first layer of fully connected layer, input is the 120. And then also we apply the reduction of the element, and next fully connected layer we have 84 numbers, and finally we have 10 output from 0 to 9. It is also has to be connected, and at this stage we apply the soft-to-max function. I'm not 100% sure, but this is what I remember, that at the first stage of convolution, filter size is 5 by 5. Input vector is 32 by 32, and the filter size 5 by 5. And then mathematically 28 is coming from 32 minus 5 plus 1. So I checked it, and what I found is that this convolution size is 5 by 5. And also I found that pooling, during the pooling operation, the window is 2 by 2. And at the second convolution, what I found is that filter size is again 5 by 5. By applying the 5 by 5 filter to the 14 by 14 matrices, 10 is equal to 14 minus 5 plus 1. Then that is the size of output of the convolution. Then again, we apply the 2 by 2 pooling layer, output will be 5 to 5. And then this 5 to 5, 16 or 5 to 5 matrix will be connected to 120 fully connection layers, and then 84 fully connection layer, and finally 84 fully connection layer will be connected to 10. At each stage of this operation, there are a lot of weight matrices in the filter and also fully connection. So these parameters will be determined and updated during the back propagation. this is very simple CNN structures, but still it worked very well. And you can practice this in using the TensorFlow, and still it works very fine. And at this and that was about more than 20 years ago. And right now CNN is more developed, and I look at the publications, and probably current CNN architecture is complicated and more complex, maybe 100 times, 1,000 times than this one. And as I told you before, that is enabled by the help of computing power called GPU. Now let's talk a little bit about the filter. That is very important part of the design, and it will have Wij parameters, and those will be updated during the training process. So initially, automatically, after the training process, this convolution filter matrix will be determined. Let's assume that after the training, let's assume that your filter, convolution filter, has this shape form. And this means that probably those convolution filter will extract the lateral feature. At the beginning of my class, I show you that this matrix will be trained, and finally you will obtain such a matrix form. And then I assume that then matrix form has this shape. That means that convolution process and filter function is to identify the lateral feature. After the training, let's assume that your filter has this kind of vertical shape. That means that filter's function is to do vertical feature extraction. Personally, I haven't done the CNN model and training. If after the training, if I had a chance to look into the matrix, filter matrix, probably we can imagine what are the function of this filter matrix. And I think those are the approaches of image recognition scientists. But I haven't done that personally, but this is my mathematical interpretation of filter matrix used in convolution operation. Also, we can think about that probably if you have a circular shape of the filter numbers, and then probably this will work as a circular feature extraction. What I'm trying to do right now is, what is the goal of filter and convolution? Why this CNN has been devised at the beginning at more than 20 years ago? This kind of idea came from vision signal processing society. If they want to extract some feature, let's assume that you have images of your own. During the weekend, you may take some pictures of yourself and friends, and maybe you could take pictures at the restaurants. Let's assume that you have images, you have a set of images, and please apply this mathematical operation of this matrix and this matrix and these matrices. And you will find out that after applying these convolution matrices to your images, you will see that certain change of images, and you can find that if you're applying this number one matrix, lateral image will be more emphasized in your image. And if you apply this vertical features filter, you will amplify more vertical images. And probably you apply this convolution operation to your images, probably circular nature of your image will be more emphasized. That is the conventional signal imaging methodologies. But in CNN, probably we got insight from those approaches, and those ideas are included in convolution and pooling operation of CNN. Probably 20 years ago, when people started to make a CNN machine learning model, they got idea from the signal imaging process. Let's assume that, for example, let's assume we have these images. If you apply this convolution to this section, let's assume this section is the 1, 1, 1, 1, 1, 1, 1, 1, and you apply this lateral convolution filter, you will get 1, 1, 1, 1 multiplied by 1, 1, 1, 1 is a kind of dot product. You will get number 5. But however, let's assume that you have image of this section of number 7 writing, and then only we have 3, 1, 1, 1 at the corner. If you apply this lateral feature filter, multiplication of this convolution of these two matrices, because 0, 0, 1, 0, 0, 0, 0 at this section and 1, 1, 0 section, output will be 0. So if by applying this convolution, number 5 means that this section has a lot of lateral images, but 0 means that we have almost non-lateral images. So convolution will give us how much lateral images it has, or how much vertical images it has, how much square shape of images you have. By applying these convolution operations, we can extract certain features. I think that's why we are repeatedly applying the convolution operations in CNN. So now I'd like to summarize the CNN again. First, and CNN feature is that the goal of CNN is the feature extraction, and they repeatedly doing the feature extraction, and finally it will achieve the classification. To reduce the burden of computer, in the middle they are doing the pooling operation. And the CNN model wanna replace the eye and brain. That is very important part of our brain. And so there are heavy matrix and tensor calculations because the image itself has very high resolutions. As I remember, there are certain CMOS image sensor. The pixel size is, I think, more than 10 to 8. There are some companies are making the CMOS image sensors. Now the pixel size, I think, more than 10 to 10. 100 by 10 to 8. Also, some TV has 8K. So pixel size is more than millions. And pixel size of image sensor is more than 100 times 10 to 8. So, and let's assume that if you are taking movie, every second you take 60 frames in a second, and also probably you have to include the colors, and so 1 hour, 60 minutes, and 1 hour. These are huge numbers multiplied by this pixel size. So the calculation burden is quite large, and we need some computing power. And also, I would like to say basic building block and repeatedly they are connected. They are convolution and pooling operation. Convolution is majorly used for feature extraction, and there are a lot of hyperparameters such as filter size and filter numbers, and also pooling size. So there are a lot of heuristic numbers. Application could be uh, very various, especially for image processing. These are a summary of CNN. I would like to skip this part, and sometimes you need to calculate input vector size xi, and the filter size xf, and output vector size. And I spend a little bit of time to find the relationship. Output vector size can be calculated using this equation. This is input vector number. This is the padding number, zero padding, and this xf is the filter size, and this is the stride number plus 1. And you can easily plug into some numbers, and you can verify this equation. So sometimes when you are designing the CNN, you can check these numbers to make sure what should be. Using this equation, you can decide the stride number or padding numbers. And at the final stage of fully connected CNN, we are doing the flattening process. Flattening process means that just before the fully connected layer, output of max pooling, output of pooling will be a kind of two-dimensional matrix or three-dimensional matrices. And however, this has to be stretched to a one-dimensional vector. And then we can apply the softmax, and we can achieve the classification. The classification is kind of one-dimensional. Let's assume that first element of your output vector may be tiger, cat, dog. So output of CNN is the classification, and then output vector should be one-dimensional vector. Sometimes this output vector could be 0, 1, 2, 3 to 9. Sometimes this vector could be A, B, C, or alphabet or some wording. So this size will be huge. So just before applying the softmax, we have to do the flattening process. Flattening process means the first element of 2 by 2 matrix will be connected to the first element of one-dimensional vector. Of course, here also we have to find out some element, connection element. That is the linear multiplication. During the backpropagation, we have to also update this to find the optimal point. For example, this one is the W3 by 3. This is the element 3 by 3 will be connected to 9th element. So also we have to update this W matrix during the backpropagation. This process is called flattening process. Now, so far, I have discussed the basic structure of CNN and mathematical operations. Especially, I explained more details of convolution process and pooling process. Once you understand that CNN is not that much complicated, I would say compared to RNN and LSTM, CNN is a little bit more easier to understand and more easier to practice. But still, I would say backpropagation need to be discussed a little bit because we have talked about the backpropagation many times during the RNN and LSTM. I can go very fast today. Let's assume that we have a cost function J and J will have J1, J2, J3 up to Jn. In RNN, we have to add all the cost function of state T to state T. And so at the time, you remember we define J1, J2, and JT and JT. We have to optimize the connection and weight matrices by adding all these cost functions in time sequence. That is the case of RNN and LSTM. But in CNN, output will be at the same time, it will arrive at the output at the same time, and output O1, O2, O3, On is number of this element, vector element is this, for example, to identify your writing, it could be from 0 to 9. And this output will be softmax, and then we can, by applying the softmax, we can obtain Y1, and this Y1 dash might be the true value. And then by comparing that, applying the cross entropy function, we can calculate J1. By adding all these vector elements from 1 to 4, we can obtain the total cost function. So if you want to apply, if you want to find the backpropagation relationship of CNN, you have to start with cost function J1, and you have to go back to Y1 and A1. Then A1 will be connected to A11T because this is the kind of stretching function. Depending on how you design this fully connection, but I assume that this A11 is the A11T element, and A11T element is multiplied by weight W111 fully connection. So it is now very simple, and derivative of cost function with the W11, that is the connection element from A matrix to the fully connected matrix. And then we have, by applying the chain rule and partial derivative rules, we have to calculate number 1. That is the derivative of cost function with the output function, softmax output function. And usually it is a cross entropy function. And also output function with respect to the, this is softmax output function. Derivative is Y1, 1 minus Y1. Repeatedly we use this equation and this equation. Then connection between W11 and output Y1, that is A11. That is the input of A11. Of course, A11 is the activation, ReLU activation function of convolution matrix. At this moment, I'm not going to talk about, I'm going to skip the pooling layer. So input will be A11T. So this is the update gradient, this is the update equation for the fully connection layer, and that has to be plugged into this gradient descent equation. Now, let's move on to a little bit complicated case. You assume that this element, this filter, convolution filter has to be updated. Then means that you have to derive the equation of partial gradient, partial derivative from cost function and output function and a function, fully connected function, and then we have to go through up to 5. And it will go through the ReLU activation function. Again, here we can derive this equation. This is the cross entropy cost function. This is coming from softmax function. This is a fully connected relationship. Number 4 is the derivative of ReLU function. If the g is larger than 1, it is 1 because this is ReLU function. If below to 0, it is becoming to 0. We apply number 4. Number 5 is the relationship between input vector, input matrix, and convolution filter matrix and output. And those are A11, 1 minus A11. So this is the, that is the, for the case of sigmoid, that the ReLU function case, this is the case. And I spend a little bit of time to develop this equation. So now I would like to summarize my class today. How can we do the backpropagation of CNN? I think we have to find all the pathways. Right now, for the purpose of class, I only go through very simplified pathways, but using the indexes of matrix operation, we can find all the pathways A, B, C, D, E, and we can apply the total update equations. This is summary of backpropagation of CNN. We have to find all the pathways from filter matrix to the cost function, and we derive the chain rule equations. At the finally, and we have to go up to the derivative of G, this intermediate value of convolution operation, the derivative of convolution operation output with respect to the filter of convolution, and apply the gradient descent equation and complete trainings. And this operation has to be done repeatedly and repeatedly. There are huge amount of computational resources. Those are needed. Because in this semester, I want to go deeply into the reinforcement learning. So I would like to conclude this class in an hour, this class about whole CNN structure concept and backpropagation. And next week, I'm gonna talk about GAN, that is the generative model. That is also an important part of the machine learning model. And in an hour, I'm gonna complete whole classes. So I will go very fast. So please be patient and accept my apology because I'm gonna go very fast. Because I wanna spend more time on the reinforcement learning. At the end of the classes, I'm going to combine deep neural network with the reinforcement learning. That is called deep reinforcement learning. And there are a lot of mathematics and new concepts will coming out. And I hope we still can enjoy the class. Thank you for your kind attention.